Okay, the theme of our lesson number 8 is Fourier series, and we are going to use an example that's well known in engineering, which is the Laplace equation. Just get the pointer here. Second. The Laplace equation. When you solve in a finite domain, either 1, 2, or 3-dimensional domain, you obtain the differential equation that governs the dependence of the objective function on one or the other coordinate, generates, depending on the situation, eigenfunctions, and which each eigenfunction is associated with eigenvalues. So our objective is to illustrate how these eigenfunctions come by as a solution of the Laplace equation. We are going to illustrate this using the rectangular coordinate system, an XYZ system, traditional. For each system, different differential equations are generated. For instance, in Cartesian coordinates, we have we're gonna obtain Fourier series. We're gonna have an oscillator differential equation, harmonic oscillator differential equation. So we're going to generate Fourier series of eigenfunctions. If you go to cylindrical coordinates, you might get those Bessel functions as we described in the previous lesson. So in general, the equation that we are talking about is an equation that has a form of a Laplacian of a function. In electromagnetic theory, this is a well-known equation. This is the potential function that we dealt before for the point charges. Now we're going to talk about boundaries. For instance, those boundaries may be conductors that are held at constant potentials. So giving those boundary conditions, we want to determine the function in the domain. So we have the potential function phi. And in Cartesian coordinates, the Laplacian is an operator that has second derivatives, like so. And we are looking into possibilities of objective function or our potential function to be separable as a product of 3 one-dimensional functions. And when we plug this specific function into that equation, we get something like, notice that derivative in x doesn't operate in y and z and so forth. So we would have something like this, gh total derivative of f, second derivative effect, plus fh total derivative in y for the g function, and finally fg total derivative of h. And we can play with this thing here and divide by the product. That's a traditional way of doing this. So you get something like that. Sum of terms which are a function of a single variable. And notice that function that depends only on a single variable, okay? they cannot add up like this to give a zero value, whichever values of x, y, and z. Okay, that's called f, capital F, g, and x, and h. So we cannot have a sum of things that depend on specific variables like this to give a constant, specifically to give zero. So the only possibility is that either term is independent of any variable. So this has to be a constant. Okay, this also, and this also this one. So, on the constant, I mean, the choice of constant depends on the physical problem. The constant that we use is called the separation constant. Okay, so let's, for instance, call this. Let's say we're talking about the real physical problems, and so the functions we are going to deal, they are real functions. We could play with the complex functions, for instance. It could be convenient, but not for potential problems. So, okay, for instance, choose a real constant, which depends. I mean, you can choose this equals to a certain constant. Let's say a positive number, plus or minus gamma square, gamma being a real number, okay? And we can choose, for instance, so this is plus or minus, depends, I mean, the size is going to be, we're going to understand very soon. We can choose these negatives, this negative and this positive. We can use many different options, but let's say we choose let's say 1 over f d to f dx squared let's say minus that equals to plus or minus alpha square, and the minus 1 over g, let's say this is plus or minus beta square. So in fact, I mean, you can play around with this. I mean, you can show that each combination of terms like this is a constant, but the constant has to satisfy a relationship, okay? So if I make here minus, minus, and minus, this is going to be plus or minus alpha square. It's going to be plus or minus beta square, okay? And in fact, I showed this, I'm sorry, I did it wrong here. Sorry about that. Let me put separately here. So, if I choose minus, if I choose that, so I'm going to have plus or minus alpha square, plus or minus beta square, plus or minus gamma square equals 0. I cannot satisfy if I have the same sign combination, for instance, plus, plus, and plus. So I can, for instance, choose plus alpha, plus beta, and minus gamma, or I can use minus alpha, minus beta, and plus gamma. I can have different choices here, okay? I can use, for instance, plus alpha, minus beta, and plus gamma, because the same sign for all the constants is not possible. One of them has to have a different sign than the other two, because these are real numbers. For instance, for this combination here, I would have a condition, I mean, the constants have to be chosen in such a way that alpha square plus beta square equals to gamma square, okay? Let's use, for instance, this combination here for in principle, okay? This is going to generate some specific situation. Before that, but let me just say that any equation that we obtain here, whatever choice of sign I take, I mean, the equations are always going to be second derivative plus or minus gamma squared times the function equals to 0. So in general, the differential equation that governs each of these functions is of the type, I'm going to write like this, u plus minus is either choice of those functions with a given choice of sign. So each function f, g, and h satisfy something like this. d2 u plus minus. Let's say the independent variable is c, which is either x, y, or z. Okay. So plus or minus some constant, which can be any of these. Let's call lambda square equals to 0. So for one choice of sign, I have a u plus solution. For the other choice, I have u minus solution. So if we compare this with what we had in our last lesson, the Sturm-Liouville theory, we have an eigenvalue equation which is very similar as this one. Okay, we had something like this: Lu operator times u plus an eigenvalue, let's say call lambda prime, weight function times u equals 0. And recall that w had to be a positive function. A function of x could be a constant, for instance. Okay, so we said that this type of equation will generate orthonormal functions or eigenfunctions for w larger than 0 and for lambda real, okay, lambda prime. So that's what we said. So, I mean, if we have that, we have eigenfunctions that form a complete set from which we can decompose any other function in the same domain. Okay? So, in our case, w, for the equation in which I have a plus, the w equals to 1, and the lambda prime equals to lambda square. And for w equals to minus 1, because we're going to have an equation like that, depending on the choice we made for each constant. I mean, for w equals to, for the choice of plus sign, we're going to have, we can generate eigenfunctions associated to those eigenvalues. And for w equals to minus 1, which would be the other case when you make a different sign, you're not going to have orthogonal set of functions. Okay? So that's what we have here. So in fact, when you have w equals to 1 and the lambda prime equals lambda square, the solution, which is like this, the differential equation, which is this one, is in fact the harmonic oscillator differential equation, which we know the solutions. They are sine and cosine functions. Okay. So let's, for instance, let me just show you the possibilities of choice. We have a table here. Which gives the possibilities of signs for those functions, okay? So we have plus, plus, and minus. So you can choose those signs which have all these possibilities, okay? Let's look into two-dimensional problems. So you give the general picture here. Let's go a little bit back. Let's consider now that the problem is, the function is a two-dimensional function. This can happen, for instance, when you have a closed domain, rectangular domain, which the function potential is specified on the boundary, And this cross-section is kept constant on the direction. Let's say this is x, this is y. This is kept constant. The cross-section is kept constant. The same boundary conditions. Let's say V1 potential is tied to V1, V2, V3, V4, and the four boundaries. And this doesn't depend on z. So in this case, the function that governs the problem is a function of two variables, y, x, y. And in this case, if we use the same strategy of separating the function to two functions, we're gonna have also two differential equations which are very similar from those that we had. 1 over f plus minus d2f dx squared equals to plus or minus alpha squared. And the other equation is going to be similar to this one, which is going to be 1 divided by g. So I had to choose the sign properly, so it's going to be g minus plus d2g dy squared equals to minus or plus alpha squared. Why is that? Because when I sum this term with that term, the result is 0, which satisfies the Laplace equation. Okay? So that's the way we would obtain a solution. We are going to see what are the solutions of these equations. I mean, you know that one of them is going to be, we're going to generate orthogonal functions, eigenfunctions. The other one is not going to generate any complete set of eigenfunctions. So let's see what happens. So we have those, let me repeat. So Laplacian of phi equals 0. We separate phi into a product of f and g. And we said that f satisfies an equation like this with a given choice of sign. And the other one minus plus here. Minus or plus alpha square. Well, we have to consider before doing that the possibility of alpha being 0, okay? So we can have a possibility. I mean, if these are 0, we can have that also satisfies Laplace equation. So in this case, f is a solution ax plus b, and g is something like cy plus d. We can have that possibility. So this in fact can, I mean, the solution of the potential can be something like this. First, up to second order polynomial, but with a cross term, something like this, a plus bx plus cy plus dxy. We are going to work this in the problem sets at the end of this lesson, but this solves problems of this type here. I'm going to show you this type of problem here. So we have a region which is bound by a constant potential. I mean, constant potential means a conductor, okay, in an angle like this, and a function like this, which is this inverse function, in which in this region the potential is constant. If you work out this problem, you discover that in this region the general solution is of this form, and we can plot the function in this domain and see how it behaves. Okay, that's going to be left for the problem set at the end of this lesson. The interesting case is also the one that is going to generate the eigenfunction that we spoke about before, is when, second case, when alpha is different than 0. So in this case, I mean, for one specific choice, we have two possibilities. That's the one that's going to generate the eigenfunctions. The other one is going to be something like this. The minus solution. So she's a minus, W equals to -1. That's the one that doesn't generate eigenfunctions. It's going to be governed by a differential equation like this. We know that this U plus, the solutions of this equation is a combination of sines and cosines. With a coefficient, a parameter, a scale parameter here, which is the constant, which is the eigenvalue of the eigenfunction. And for the other case, the solutions can be expressed as real functions of hyperbolic sine and hyperbolic cosine, something like this. A minus hyperbolic sine and hyperbolic cosine. Okay. We could also use complex functions, for instance, I could use alternatively, I could express U plus like this. Let's make different constant here. Complex exponential okay, and also the hyperbolic functions could be expressed as a combination of real exponentials, like so. And I mean, this is not a very convenient form in the way we are describing problems which are governed by real functions. So we are not going to use this form here. This is usable, for instance, in wave phenomena, where you describe plane waves. Plane waves are better described by complex functions like those. Okay. So, but not the Laplace, the potential function, which is a real function. For real problems, DC problems, it's always going to be preferable to use the traditional real representation of the function. In the other case, those functions here can be also used alternatively using real exponentials. It's important to recall that the definition, the correspondence between hyperbolic functions and exponential function is like this. This is the difference. And the cosine is the sum of exponentials. It's important to know the behavior of these functions to understand the solutions of real problems. I'm going to point out those important properties here. We have a similar definition for the relationship between complex exponentials and sine and cosine functions. You can see that. Notice that those exponential functions, those hyperbolic functions, it's important to see the properties. The hyperbolic function, for instance, the hyperbolic sine function is 0 in the origin, okay, at x equals 0, let's say hyperbolic sine of x, and goes indefinitely, unbound as x increases or decreases. On the other hand, the hyperbolic cosine is 1, the minimum value of the hyperbolic cosine is 1. The hyperbolic sine is an odd function. The hyperbolic cosine is an even function. How do they look like? Well, look at the expression. Look at the definitions as, I'm sorry, I put a z here. It's wrong. It's psi. Let's put a psi here. Make it psi. That's, let's see. That's a psi. It's supposed to be psi. Okay, so observe that as psi is very large, this term dominates relative to this one for positive psi. So the function resembles the half of the exponential, positive exponential. The same goes for negative psi. Negative psi, this term is going to dominate, and the function resembles the exponential minus of psi divided by 2. Okay? On the other hand, cosine, as psi is too large, is going to resemble 1/2 of exponential, or in either direction. So if you look at the way they behave, I mean, this sine resembles the positive, half of the positive exponential for large arguments, and minus the exponential for the small argument. I mean, they are asymptotically equal. And the cosine is going to resemble, I didn't plot the exponential minus, which would be something like this. It's not plotted here, I'm just showing the positive branch. Okay? Well, so giving all these possibilities of solutions, the solution for two-dimensional problem is going to be something like this. I can put here the expressions easier. Let me increase a little bit this. So you're going to have type 1 solution. Probably do some notes in my. So we're going to have, type 1 solution, okay, is going to be, traditional sine and cosine function as a function of x, and hyperbolic as a function of y. And type 2 solution, which is the other possibility of solution, which is a hyperbolic variation in x, and periodic, because those are periodic functions, periodic variation in y, okay? So let's make one simple example to see how we can solve a problem, real problem, of the potential determination in a two-dimensional domain, and the boundaries of the domain are subjected to boundary conditions. Let's say, for instance, we have a region that is like this, a square region, right? So let's say that we have an earthed potential in this region here. So this is a zero potential, okay? This is like a conductor. So this is zero, like a U, okay? So in this region here, in this boundary, have zero potential, as shown. And then here we have a very specific variation In fact, I have chosen a specific variation that fits into one of the eigenfunctions of the problem, okay? So let's say that for y equals to b, so this width is a here. Sorry. This is a. Move that thing here. And this one is b. So, in this U, you have a conductor. Okay? So the potential is earthed, it's grounded. And here you have a very specific variation with the potential. It goes, the potential changes in these segments as a function of x. And you notice that in x equals 0, it's going to be 0 right in this corner here. And it's going to grow up. When x goes to a over 2, right here, the potential goes to v, which is it's going to be v volts, let's say. And then you go along the potential at x equals to a sine pi 0 again. So you have another node here. So the potential increases and decreases to 0. So there's a very specific form of the potential. So if we try the solutions, okay, if we try to use the type 2 solution, we're going to show that the solution doesn't work. It cannot satisfy the 4 boundary conditions for this type of solution here. And the reason is very simple. These are hyperbolic functions, okay? So in general, a hyperbolic function, when the sine function has only one root, the cosine function that has no roots, okay? I could probably conveniently combine those two functions and find more than one root for this problem. But in general, when you have as a function of one of the coordinates, which is x, the potential repeatedly goes to 0, like this. In x equals 0, the potential 0 goes again to 0 in x equals a. If you try to use type 2 solution, it doesn't work. Cannot satisfy all the 4 boundary conditions. Please try using it. Okay, I'm going to make an exercise quickly here. Let's try to see if it works. Okay, so in x equals 0, this function is 0. So I have, let's try type 2 for that problem. In x equals 0, we have a sine, which is 0. It's going to be b cosine of 0, cosine, hyperbolic cosine. So you're going to see sine so we try that. We have this equals 0, whichever value of y between 0 and b. So we try that. This is 1, okay? So the only possibility of making this 0 without making the function a total null function is to make b equals 0. So we can choose b equals 0, okay? So that satisfies the boundary condition at x equals 0. So now our function is something like this. The a sine a times c, which is the constant that was in front of the hyperbolic side, a times c, I'm going to call c prime. Sorry about that. Sine alpha y plus d prime cosine. Now we go to y equals 0, where the potential is also grounded. So we go to y equals 0, x changes from 0 to a. So y equals 0. So this term goes to 0, this is 1. So we're going to have d sine, hyperbolic sine of alpha x times 1 equals 0. So this function can only be zero in the origin, but x is variable, so I have to impose g equals 0, so this term goes away, okay? So our function now is reduced to this constant c prime, hyperbolic sine, sine of alpha y. Now I go to x equals to a. Okay? So I have to impose that the potential again is 0 at x equals to a. So I'm going to have c prime hyperbolic sine of alpha a times sine of alpha y. You notice that y goes between 0 and b. So this cannot be 0 all the time, only at y equals 0. This has to be 0. I cannot have this 0 without making 0 the argument. If it make the argument equals 0, alpha has to be 0. If alpha is 0, the whole function disappears. So the only possibility is alpha equals 0 or c prime equals to 0. But if I do that, our function becomes the trivial solution, okay? But notice that the trivial solution only satisfies those three boundary conditions here. Those boundary conditions in the U of the boundary, but it doesn't satisfy the specific condition on the last segment of the boundary, of the domain, okay? So type 2 solution, which one, the one we tried, doesn't work. So if we try to use the type of solution, then we have something a little easier. I mean, you know that I can apply the boundary condition at x equals 0 and y equals 0. I'm going to have a reduced form of this function, type 1. Let's just go, I can just move on, go a little faster here. But we're going to have now a reduced form, already satisfying potential x equals 0 and y equals 0. So a function that satisfies those two is going to be something like, let's see, how did I call? I'm going to call, let's see. I'm going to call something like this. A, forget about the name of the constant, it's just a constant. Sine alpha x, sine, hyperbolic sine alpha y, because this is a type 1 solution. So you notice that this function is 0 for x equals 0, is also 0 for y equals 0. So now we go to x equals to a. We move on to x equals to a. So we're going to have a sine of alpha a, hyperbolic sine of alpha y equals 0. Recall that y is between 0 and b. Okay? So now I can have two possibilities. A equals 0, which is going to kill the function. We don't want to do that. The other possibility is sine of alpha a equals 0, right? Now in this case, I can have this equals 0 without killing the whole function. It's sufficient to do alpha a equals a multiple of pi, m pi. M different from 0, because m equals 0 makes a 0 function. I don't want to do that. So this is going to be indexed by a discrete variable m. So we have an infinite discrete set of infinite possibilities of alpha that can satisfy the three boundary conditions without satisfying the last one yet. So we have that. So in fact, what we have now, we have found a response to an unknown that we had, which is the eigenvalue, or the possible eigenvalues of the solution. Okay, let's go back here to our virtual blackboard. So now, we're going to have alpha MA equals M pi. In fact, M is enough for M to be positive number. Negative numbers just reproduce the same function, okay? We call that the eigenvalues are the square of alpha. So positive and negative numbers give the same eigenvalue, right? So we have to choose alpha as a discrete set given by this expression, okay? And with that choice, we have a solution. Let's call it phi. Let's index the function by the discrete variable m. We have an infinite set of possibilities. A set of infinite possibilities, which is something like this. Sine of m pi x over a hyperbolic sine of m pi y over a. Now we want to satisfy the last boundary condition, which is to impose that the solution fits into this last one here. Okay. So we have to impose that the solution at y equals b equals to v sine px over a. So y equals to b, we have am sine m py pb over p, I'm sorry, mpx over a equals to v sine px over a. So if you look at those things, the only possibility of equaling those two is to choose the same scale factor here. So 1 pi, m has to be chosen equals to 1. So only one of the possible solutions has to be used. And when you make m equals 1, you have to choose the constant a1 sine, hyperbolic sine of pi b over a equals to v. So if I do this choice, I solve the boundary value problem. I solve the differential equation subject to the boundary conditions. So that's the solution for the problem. Something like this. V volts, in general, the potential function is given in volts in the SI unit system. So it's going to be V divided by hyperbolic sine. So that's our solution, okay? Something like this. That's the final solution that satisfies all boundary conditions. This function has a behavior, and we can plot, we can use MathCAD to plot this function as a function of two variables, as we did before, having the y, the z-axis is going to be this function space. We're going to have the z axis is going to be, in fact, this is not a geometric space, this is function space. It's a phi as a function of x and y. So we can plot in the domain in which x goes between 0 and a and y goes between 0 and a. In this domain here, the rectangular domain, so this has width b and this has width a. So we can plot the function, and if we look into the function, it's going to be something like this. Now, just show you the picture that you can see that in MathCAD. You know, I mean, this is in fact This is y. Okay, this plot here, this is y. And this is x. So this is the function in x, in y equals 0 here. This is right here, y equals to b. So in b you have an arc like a sine, you know, something like this. You can see the potential function as a net that is stretched between this arc, you know, this round arc here, going down to the boundaries where it's going to be 0 height. Okay? So you can look into a soccer goal, you know, that has a sine profile in the goal. Have a net here that's stretched between that rigid arc and the other segments which are rigid. That the potential is held and 0 value in the boundaries here, and has a sinusoidal profile in y equals to b. That's the behavior. For the potential function, we can do, I mean, determining electric field lines and so forth. They're going to talk about it later. But just to show you what's the physical interpretation, okay? I mean, if you make a cut, you're going to have a constant potential, equipotential lines like this. You know? You're going to see those equipotential lines. You have equipotential lines, and they're going to have orthogonal to this line, have field lines. But we're going to talk about that later. Now let's go on. This is what happens when you have well-defined potential. In fact, I showed specifically the potential to look like one of the eigenfunctions of the problem. Okay? But suppose now that you have an arbitrary profile in y equals to b. Instead of being a sinusoidal profile, now you have an arbitrary function. So what happens is that when you go to y equals to b, if you get those type of functions, phi m, let's go back again. If you want to impose in y equals to b, okay, so what I get in y equals to b is a function that is, a single function like this is going to be a periodic function in x with a well-defined periodicity that is governed by this scale factor here. So in y equals to b, you're going to have something like this. am sine, a parabolic sine of mpb over a sine of mpx over a. And I want to make this equals to fx. With fx is an arbitrary function which I, in fact, don't know what fx is. Okay? So I cannot satisfy this problem with a single function like this. The single function is a periodic function. These are arbitrary functions. So what can we do? We can superpose all the possible solutions and try to force that this combination converge to fx. Okay? You notice that if a single function is a solution for a Laplace equation, a sum, a linear superposition of functions is also going to be a solution of Laplace equation. Okay? So what we do is to propose that the solution is not only a single one, but a combination of all possible solutions. And that's when we're going to get to the point of decomposing a function into eigenfunctions. That's how we get to that problem. So recall that those functions are solutions, okay, of a Hermitian operator that has eigenfunctions, which are orthogonal in the domain X between 0 and A. This is the property of this function here, okay? If I make y equals to b, I want to force that f equals to the sum. It will be something like this. Where Cm is just a constant. So Cm is just this constant here, okay? Which is an m-dependent variable. So what we have is this. F is a decomposition of Cm times Um, where Um has an orthogonality property. If you notice, if you see, the Um are all functions that have a node in x equals 0 and x equals to a. Okay, that's m equals 1. That's m equals 2. These are the solutions for the harmonic oscillator problem, right? M equals 3 and so forth. So these functions have orthogonality that's well known. If the domain is 0 is smaller than x, smaller than a, if I define this the dot product, recall that our weight function, the definition of the dot product is 1. So this is these are real functions. There is no complex conjugate here in the terms defined in lesson 7. So it's un dx. If we calculate that, it's going to be equals to 0 for different indices. And it's going to be a over 2. This is between 0 and a. It's going to be a over 2 if the indexes are equal. Okay? So this is very well easy to calculate. So, I mean, if we define the dot product is function space as we did in the previous lesson, as this, sorry, it's a little slow here. If we define the dot product like this, I mean, between two functions, f and g, this is a non-normalized eigenfunction, okay? F of x. G conjugate, but these are real functions, so you don't have to make a conjugate here. So this is the same. Remember that W that governs our emission operator equals to 1. So we would have a W here in the definition, but W equals to 1. So remember that Um dot UN equals to A over 2 delta Mn. Delta is the Kronecker delta. Okay, so if you make that, you can use easily, you can easily find the coefficients. I make a dot product with function space in each side, so I'm going to make this is m, and I'm going to make it specific m. Well, let's call un, which is one of those values here. So during the linearity property of this function, it's going to be something like this. And this is a over 2 delta mn. So we have a single element in the sum that satisfies this condition. It's going to be Cn a over 2. Then I have the coefficient. I solve the problem. All I have to do is calculate this dot product here in function space, which is, in fact, the integral between f, which is going to be specified for a given problem, and the eigenfunction, which is sine npx over a dx. Okay, so that's the solution. Once you obtain Cn, you're going to have An. So Cn is An times parabolic sine, so it's going to be Cn, which is calculated here, divided by parabolic sine. Which is 2 Fun divided by A parabolic sine. So that's the solution. I mean, we find now the solution of the problem for any function. So any problem in which you have a boundary like this, okay, in which we have a U, let's say, a conductor, okay, have a conductor here, and a conductor here, make a conductor region, conductor there. Okay, so we put, let's say, conductors in the boundary. So we have all conductors here. So we impose, I mean, this specific problem in which the potential is grounded in these conductors. Talk about electrical engineering, right? So the potential function here, whichever is the function you specify in this boundary here, the solution is obtained as the prescription I just gave you. I mean, you expand the solution with coefficients given by this expression here, and the solution is going to be something like this. Something like that, okay? So that's how we solve the problem. And now, we can move on to solve any problem with any arbitrary functions. You see that we can solve any problem in which a U-shaped region is grounded. But the U-shaped region can be here, can be like this, or can be like this. It can be any type. So I can break the problem if I have a problem that has arbitrary boundary conditions on the 4 segments. Okay, let me just move on here. Let me just find the page quickly here. So if I have an arbitrary problem, if I have a problem like here, let's see. No, it's not there. So I have a problem in which the potential is given. I mean, I can solve a problem in which I have a U like this, arbitrary function here, F. So I have if I have a problem in which the potential is arbitrary, let's say F1 of x in this boundary in y equals 0, F2 of y in x equals to a, F3 of x in y equals to b, which is here, and F4 of y. So if I make arbitrary function in the 4 boundaries, what I have to do is to break the problem into problems with a U-shaped grounded structure. For instance, F3 would be would have a U like this. Okay, so I can break in simpler problems like this. I mean, have this complex problem here. Can break, for instance, here the U is here. Okay, that's the U. where the potential is grounded. So I solve this problem, it's easy to solve. The solution is going to be a periodic function in x and hyperbolic in y. There's another problem that's similar here. The U is like this now. The grounded structure is here. So I have an arbitrary function in y. Now I have a periodic function in y and hyperbolic in x. So I solve the simpler problems here. Okay, this is the one we just solved. I have a U-shaped grounded structure here, and periodic in x, hyperbolic in y, and finally have a U-shaped region like this, grounded, have a periodic in y, hyperbolic in x. So we solve the functions phi1, phi2, phi3, and phi4. If we can easily show that the solution, the final solution, is a superposition of these four solutions that are easy to determine. So the final solution is going to be the sum of the four solutions. So with this strategy, you can solve any problem. And notice that the periodic solution, I mean the arbitrary function, is decomposed as a superposition of orthogonal eigenfunctions. The eigenfunction is the eigenfunction of the harmonic oscillator problem. Okay? Now, if we go back to three-dimensional problems, I mean, you can make also a similar methodology. You can solve a problem in a tri-dimensional domain like this. Now, x goes from 0 and a, like this. Y goes from 0 to b, and z goes from 0 to c. Remember that the separation constant has to have two equal signed constants, and the other has an opposite sign. I mean, for this specific problem, we're going to see that in x, the solution has to be periodic. So that's one given choice of the sign. In y also, the solution has to be periodic. And in z, the solution is hyperbolic. Okay? So if I have an arbitrary function as z equals c, this problem here, okay, we can satisfy all the 5 boundaries, excluded that one, if we choose, okay, harmonics like this. I mean, the only difference is in z you have I think this is wrong. There's no pi here. Okay, no pi there. Just hyperbolic sign of gamma z. Gamma is indexed by 2 integers, m and n. Where m and n come from? Well, come from the solution that we obtained for the x and y functions. The x, y now is a product of 2 eigenfunctions. Okay? So this alpha, this is beta, m pi over a is alpha, n pi over b is beta, and now gamma has to satisfy this condition. I mean, given those integer values, gamma is given by the sum of the square roots. Okay? So this satisfies all the boundary conditions of the grounded surfaces. Okay? So all the grounded, if you test that, x equals 0 is 0, x equals a is 0, y equals 0 is 0, y equals b is 0, because it's sine function. Z equals 0, the hyperbolic function is 0. Okay? This function is 0. So the last boundary condition is on the top surface. And if you have an arbitrary function there, again, we try an infinite superposition of solutions. Okay? We propose to use a superposition of all possibilities. Now we have two indices. And we impose that, let's call this UMN. Hide this thing here. So this is going to be called UMN, which has a definite, well-defined orthogonality properties in the two-dimensional region x between 0 and a and y between 0 and b. So if we impose that at z equals c, we impose that the combination of solutions equals to that function. Okay. So again, we make a definition of that Cm n is a times the constant in z equals to c. So we're going to have now so we have the function z equals c f of xy, which is the function that is unknown, equals a combination in mn. Let's make it like this. M goes from 1 to infinity, n from 1 to infinity. C, mn, and our function is umn of xy. What is umn? Umn is simply those harmonic functions. Sine in x, m pi x over a, sine of n pi y over a. Okay. And then these functions have definite, well-defined orthogonality properties. If we define in the two-dimensional domain, have two functions, let's say f and g. The definition now is two-dimensional integral. So that's the dot product now. fxgy, fxy. F and g are two-dimensional functions. So this is the definition of the orthogonal of the dot product in the two-dimensional region now. Okay. So again, our functions have w equals to 1, so we don't have another function here. So this is the area element effect in the xy plane. So you see that umn, um prime, n prime have orthogonality, well-defined orthogonality property, which is something like this. It's just a generalization. So if we do that, we easily determine the coefficients again, right? So it's easy to calculate now. Just make a dot product on each side of this expansion here. With one of the eigenfunctions, we're going to find that Cmn equals to phi dot product with umn divided by AB over 4. So it's 4 divided by AB times that. Okay, so that's what we find. That's the solution. From this we can get the AMN, which is just simply divide that by the hyperbolic sign. Okay, so this is what we have to show me how to solve these problems. Now consider that we are going to make simulations in MathCAD, and we have to truncate the series expansions to try to see how to calculate. I cannot have all the terms in the expansions, right? Cannot have an infinite number of terms in the expansion. So I have to truncate, have to interrupt the series, and that's going to be that's going to generate some defects For instance, if we try to expand a constant function, for instance, okay, just to give an example, the finite number of terms, you're going to see that, for instance, if we have a function of x in the domain between 0 and 8, try to expand a Fourier series. In fact, what we have here are a Fourier series of one-dimensional functions and two-dimensional functions. If we expand as a Fourier series, that's what we did so far. So you're going to see that we're going to have some imperfections here, okay? So it's going to be something like this. This ripple starts to decrease as the more and more terms are added to the series, okay? We have an overshoot here, always. That's Gibbs phenomenon, because of the high variation of the function. It goes from 0 to a high value. So I always have that overshoot. But in general, as you put more and more terms, you're going to have a very well good approximated solution to the problem. So the workshop that we have for you, have planned for you now, we are going to have to calculate the potential function and together with the E field, okay? So given the potential function, the E field is calculated by this formula here. So E field is a vector, and from E field we can plot field lines, okay? So you're going to have a function which is going to be an approximate function, not going to be a perfect solution, but it's going to be approximate, and for that we're going to get the E field. The x component of the E field is the x derivative of phi, the y component is the y derivative of phi, and so on. So we have a lot, I mean, the first part of this workshop, of this assignment, is going to do, as always, you have to do traditional homework, pencil and pen and paper, okay? So you're going to work out some solution of the problems analytically. You're going to obtain series expansions and so forth, because these solutions are going to be used to make simulations in the second part. Okay, so there's a number of problems that we have to do. It's shown here. Okay. I have several boundary value problems in which we have to obtain a solution, a closed form solution. But all solutions always have a series of terms. So you have to find those series. And in the second part, I mean, also we're going to have to solve the problem in a tri-dimensional solution. Okay, so we're going to solve that problem too. For instance, just to give you a hint, I mean, when you have, for instance, a two-dimensional problem in which the potential is grounded in the U, for instance, let's say like this. We have a U region here in which this is a single conductor, in which I ground this U here, okay? So this zero potential, or a constant potential, let's say V equals to 0. So this is grounded. And you come with another conductor here, very close to that, almost close to the region. Let's assume that for all practical terms, this thing is very negligible, this distance. So I have a V volts here, another conductor there, okay? What is this? What is our function that models this problem here? That's the region of width A, and this is the height B, okay? Potential is 0 in here, and the potential is constant here. So the function of fx is the constant function equals to V. So for this problem, your expansion is going to be expansion of a constant in a series of Fourier terms, and you have to determine the coefficients, okay? For instance, in the three-dimensional problem that we have, for instance, you close the top surface with a conductor, and just delete all this. So we have a problem in which you have a three-dimensional region. So all of this is grounded. So we can make a conductor on the top, which is V volts. So now your function fxy is a constant function. You have to explain that function in terms of Fourier series. Okay. So in the second part of the assignment, what you have to do, have several objectives. We want to investigate in which way the graphical representation of the potential and its Fourier series approximation, how do one resemble the other one as you truncate the number of terms. Okay. We also want to look at three-dimensional problems. We want to look into how the function, suppose we have this problem here, okay? If you take slices in this region here, have a slice here. So the potential changes in this XY region here. And as this plane goes up and down, it have different behaviors. I mean, the function behaves differently. So we want to make a continuous transition of this plane from 0 to C, changing from 0 to C, and see how the potential continuously changes from the 0 value up to the constant value here. So we're going to do some animations too. So this is the other objective. And also, we want to make we want to trace field lines given by that formula that I just gave you. The E field is the gradient of the potential. And I give you the formula for that. And we want to now make field lines, okay? And also in the two-dimensional and three-dimensional regions. Okay, now we're going to have some very beautiful pictures that we can generate. When you go to trace field lines now, it's going to be a little different. Before we did field lines for point charges, we were very concerned in going away from the charge. Now we're not going to have that problem. We don't have singularities in the field anymore. So we don't have very severe problems now. All we have to do is when we trace a field line, either in two or three-dimensional regions, we have to make sure that the field line doesn't go out of the domain, okay? You can start a field line, let's say this is a positive potential, let's say V volts here, and here is grounded. We start in a point of the positive potential goes to the inner part of the front of the domain. Okay, so you start making the field lines. It has to go from the positive. I mean, you can define. I mean, let's say that you have a two-dimensional region. You can define your initial points on this segment here and guarantee that the field line go inside, inside of the domain. Okay. And also you're going to have to do that can do that in three dimensions. Okay? Recall that the field lines in conductors are always orthogonal to the conductor. For instance, they have to end like this. I mean, your solution, you're going to see if it's correct. If you see that their field lines, they really end orthogonally to the constant potential regions. Okay? So it's going to be something like this. If there's our conductor, it's going to have something like that. I mean, this has to be orthogonal when it ends in the conductor. So we have to establish strategies, computational strategies, that guarantee that field line, when they encounter a surface of the domain, it stops, doesn't go away. I mean, the field line cannot go away, go out of the region. It has only to be confined to the inner part of the region. Okay, so that's what you're going to do. We have to do have to be careful in bends, as we pointed out before. Sometimes if there's a bend, you have to take care of that. You have some prescription for that. So now I'm going to have more independence to make those simulations. Okay, so I have some animations there. So this is what we have for this just come by my office and we can discuss any questions you might have. Thank you.